Hi, can you hear me? Anybody? Can you confirm that you can hear me?
Yes.
Okay,
Yes,
we'll just start in 1 minute. Okay, we'll start while people are still joining. Yeah, sorry for the last minute change of plans. Actually, I should have checked yesterday only whether the classroom is available. But today morning I called Sagar and checked. Good thing that I called him. If I had not, we would have all reached there and then you would have seen that no classroom is available. But yeah, hopefully I'll do it next time in advance. Okay, so we'll continue with geometric transformations. I think last time I had asked you that whether you already know about homothety. I think some of you knew, but not everybody. So I'll quickly cover homothety, and then after that, I want to solve a very interesting problem, which is even I didn't think of this problem earlier, but based on what we did last time, like we saw one construction problem last time, right, where we were trying to create an equilateral triangle where one vertex is fixed and other two vertices are on two given lines. So naturally, I was thinking that what if we extend that to a square? Like I want to create a square where one vertex is fixed and other vertices have to be on some given lines or something like that. So in that, I started to think that what can be possible. So I could solve the problem, but maybe if somebody has a better solution, I would like to look at that. But at least I would like to share the solution which I have because it is a very interesting problem and it is going to give me a chance to talk more about complex numbers. Like even in from last couple of lectures, I've been mentioning that complex numbers and transformations have a lot of close connection, but didn't get really a chance to show that in a problem. So I think this would be a really good candidate. So let's do that also. Just a minute. Okay, so I hope you can see my screen. Yeah, so let me start by just recapping all the transformations you have learned so far, and I will highlight the connection between those and complex numbers. So let me make this kind of a table that so what can be the table that we make? So first is the of course the name of the transformation, like for example translation. Then what are the inputs required? Like what are the what is the information required to define that transformation completely? So we need to specify some vector, let us say AB, or let me call it vector OA because I'll always refer to the origin as my starting point. As you may already know from physics that you can move the vector around in the plane without changing its magnitude and direction, and it is still the same vector. So we can choose the origin as my starting point. Uh, then So what is the corresponding complex function, right? That if what is the transformation doing in terms of complex numbers. So for example, if z is the original point, then after applying this function, z becomes z plus a, right? And the convention which I have already established last time is that we use capital A and small a to refer to the complex coordinate and the point, right? So this is the point, then small a is the complex coordinate. In other words, A will be written as x plus iy, where x and y are the like traditional 2D coordinate system. The coordinates of A will be x comma y, but in complex numbers we will represent it as x plus iy. So therefore, translation is just adding the vector plus A to the original vector set. So this is what we studied at the very beginning. Then we also talked about rotation. So in the rotation, what do we do? We need the center of rotation, which I'm going to be assume here as O, but in general it can be any other point also. But and the angle of rotation, which is theta. So then we have studied that this is just multiplication by cos theta plus I sin theta, or which we briefly write as cis theta, right? So just multiplying by cis theta will give the same operation. Okay. Then we also saw reflection last time. So reflection again requires reflection in a line. So in for now I'm going to assume that the line I'm talking about is the x-axis. Okay. So reflecting in the x-axis. So does anybody know in terms of complex numbers what could be the corresponding operation called? Anybody knows the name of that operation? So what does the diagram look like? If this is my xy coordinate system and z, this is the original point z, okay, capital Z, whose complex coordinate is small z, and I'm going to reflect it in the x-axis, which means its mirror image is going to be somewhere over here, okay? If I call that z dash, okay. So if I write the explicitly, right, the real and imaginary parts, then if z is given by x plus iy, what will z dash be given by?
X minus iy.
X minus I, right? Because the x coordinate will remain the same, right? Every point on this line has the same x coordinate, and the y coordinate has simply reversed. So the z dash is x minus I. So there is a special name given to this operation. It is called conjugation. Okay. So this is a operation done on complex numbers, and it is denoted by a bar on top of the. Okay. So z bar is the called a conjugate of z. Okay. So z bar is x minus I. So if z is x plus iy, then z bar is x minus I. Okay. So in that notation, I can just denote this by z bar. And the important property of this conjugation is that just as mirror image is reversible, conjugation also reversible, right? Because z bar is another complex number. So I can ask you what is the conjugate of the conjugate. So it is going to be the original number again, right? So this conjugation is an important operation that you can do on complex numbers because it has a very important property that it distributes with addition and multiplication. Okay. So this is your homework to prove that conjugation distributes over addition and multiplication. So what does that mean? That if you have two complex numbers a plus b and I take the conjugate of the whole sum, it will be the same as a bar plus b bar. Okay. So this is easy to see maybe because it is clear that the x coordinate and y coordinate can be separated out and you'll get it. But what may be less obvious is that even product behaves that way. So a into b bar will be also a bar into b bar. Okay, so this is making it very useful because easily if you have a very complicated expression like a plus b plus c into d plus whatever ef, anything like that. And if you take the conjugate of that, you can simply, split up that conjugate bar into smaller bar. It will be just a plus b plus c bar into d bar plus e bar f bar. So like that, it is very easy to apply the conjugate that way, and even like pull it out. If two, three terms all have conjugates, you can make it common and bring it out. Okay. So then that way conjugation is a very nice operation actually. Okay. So so you see that how all the transformations we have seen so far have a very nice interpretation in terms of complex operation. Okay. And you can use this idea to prove some of the results which we already done so far. Like whatever we have proved that combination of two rotation is one more rotation, or two reflections is if you remember that two reflection is either a translation or a rotation based on whether the two lines are mirror images of each other or not. And I mean, you have to think in terms of here the operation is terms of x-axis only. But if I have given some other line, then what? How can you describe the reflection in that line? So you have to do some operations that you have to first rotate that line to coincide with the x-axis, then do the reflection, and then move the line back to the original position. So there are some additional steps involved, but you can think that in principle all of that can be done. Okay, so that is why this is very powerful. Okay, so these were all the congruence transforms, right? Well, from the beginning, we have been saying that all of these operations do not change the size and shape of the object, so we call them as congruence transforms. Okay, and it is a like a good result to try to prove that using these operations together, you can take any object in the plane to any other congruent object, right? So if triangle ABC is congruent to triangle DEF, then no matter where the two triangles are located, through some combination of these operations, you can start from the first triangle and reach the other triangle. Okay. So today we are going to look at extension of this. So two operations which we are going to add to this list today. So one is called homothety, okay, or sometimes it is also called dilation, okay. And what is the input required to define homothety is again you need to center. So just like rotation required center, for homothety also you need to pick a center and you need to pick a ratio. Okay. So some ratio uh, and which is a real number. Okay. So any real number has to be picked as the ratio. And then we'll see that what does this homothety do exactly? Why is it so useful? We will see all of that. I hope this conjugation part is clear, that what is the definition of conjugation and some properties which you can try to prove on your own. Okay, there are some more properties of conjugation also which are interesting. Maybe if we have time, I'll talk about them. Like for example, just to mention one usefulness of conjugation is that you can get the real part and imaginary part of a number. Like if z is x plus y, and for some reason you need direct access to x, right? So think what will happen if you do z plus z bar. The imaginary part will cancel away, right? So this is just the real part. And similarly, if you subtract z minus z bar, you will get the imaginary part. So you can sort of split the complex number into its components if you really want it that way. So that can be achieved through conjugation. And one more interpretation of conjugation, I think worth mentioning is that in terms of the what we call the polar coordinates, right? Because we can denote the same value as magnitude and angle, right? Distance from the origin and the angle theta. So what you will notice is that z bar, what will be the coordinate of z bar in the polar system? What do you think the polar coordinate of the z bar will be? Because we are measuring the angle like this. So if this is theta, then will the distance from the origin change if I take the mirror image? No, right? So the distance is going to be the same. But what about the angle? What will happen to the angle? So purely measuring in terms of geometry, these angles are both theta and theta, but I need to attach a sign to that, right? So I should attach a minus sign to this, right? So if I say minus theta, it means I'm traveling clockwise, right? So now depending on, I mean, how diligent you want to be, that you can write it as minus theta or you can write it as 360-degree minus theta, okay? Or 2 pi minus theta. So multiple ways of writing it, but basically it is going to be r theta and r minus theta, okay? So you see the magnitude remains the same, but the angle changes sign when you take the conjugate. Okay, so these are some additional points about conjugates. There may be more also. I have to think and add them, but all of that you can discover based on the definition. Like the basic principle is just the definition. Everything else follows from that definition. Okay. So, like for example, here you'll notice that if I multiply z into z bar, what will happen? So that is again a homework for you. See what happens when you multiply z and z bar. What is the answer that you get? Okay. So yeah. So let us look at homothety in more detail. What is homothety? So first thing to mention is that homothety is not a congruence transform. It is what we call a similarity transform. Okay. Okay. So under homothety, the object is not guaranteed to remain congruent to the original, but it will remain similar. Because what we do under homothety is that if we have defined the center of homothety O and the original point is P, under homothety, what will happen is P will go to new position P dash such that the ratio of the new point to the old point, the distance from the O, is that constant which you picked. Okay, so this OP dash upon OP ratio is going to be that constant K. Okay, and so this is a picture when that K is positive and greater than 1 actually. So if you see here, because K is greater than 1, so the distance is increasing, right? If OP was 2 centimeters, OP dash will be maybe 6 centimeters or 7 centimeters. But the ratio will always remain constant. And so now imagine that as the point P moves on some set, right? If I draw any set over here, okay, so P point is going to travel on this set. The image P dash is also going to travel on a set, but because everything is magnified, right? You can think of this like a magnifying lens. So everything will get magnified by that ratio K. So the object that P dash is going to move around is going to be a magnified version of the original object. And maybe the to more accurate diagram will look something like this. Because what will happen at the extreme end, right? If you draw tangents over here, so those tangents will meet at the. So it is really like a the shadow of an object or the magnified version of an object. Okay. So that is what homothety does very basically. Okay. So just to illustrate few more examples of homothety. So homothety, and as I said that you can apply homothety of any ratio. So let us say I start with a simple example homothety with ratio 2. So if homothety of ratio 2 is applied to a triangle, okay. So O is my center of homothety, ABC is my original triangle. So I can take every vertex and just double it, right? So I'll extend OA to OA dash such that basically A will be the midpoint of OA dash, right? Because the ratio is 2 is to 1. So OA dash upon OA will be 2. And the same will be applicable for all the other points. So OB will also be extended to OB dash and OC will be extended to C dash, right? And so if I join the A dash, B dash, C dash, so you can clearly see that the new triangle we have obtained is not congruent to the original triangle, but it is similar because all the ratios are going to be constant, right? Okay. So therefore, I mean, you can say that triangle A dash, B dash, C dash is similar to triangle ABC with ratio 2 is to 1. Okay, so this is the straightforward case. Just as in all the examples we have seen before, there is an identity transform, right? A transform it does nothing. So in homothety also, can you think of what is the transformation which will do nothing,
Ratio 1.
right? Ratio 1. So homothety with ratio 1 will basically move every point to itself, right? The ABC will be the same as A dash, B dash, C dash. It will do nothing. So you can compare it to rotation with angle 0. You know, rotation with angle 0 does nothing. Translation with vector of length 0 does nothing. So this is a trivial case. If k that ratio k is 1, then this will happen. What about so if the ratio is less than 1, right? If the ratio is less than 1, let us say ratio is 1 by 3, then you see now it will not increase the size of the object, it will reduce the size of the object, right? So the picture will look something like this, that your original triangle is like this. Then after you apply the ratio 1 by 3, so roughly speaking, your new triangle will be maybe something like this, right? So the original triangle ABC has been reduced in dimension to a smaller triangle. So homothety can do both. It can increase the size, keep the size the same, reduce the size. Uh, what about negative ratio? What do you think would be right picture to draw? Suppose I say I want to apply homothety with the ratio -1. What do you think the picture will look like? So in your mind, think that you reduce k, keep reducing k. So in this diagram, right, as your k is going closer and closer to zero, this triangle A dash B dash C dash will keep on shrinking and it will keep on coming closer to my origin. When k is zero, yeah, important special case. If k is zero, the ABC will entirely overlap on O, right? So that will not be very interesting. So if you keep taking the process further, what should happen? So one way to define that case is that we invert the diagram in the O. So in other words, I mean, you have seen this diagram with magnifying lens. So magnifying lens can produce an inverted image of the original, right? So if all the OA, OB, OC rays pass through O and go to the other side, right? So I'm going to take A dash over here such that this is equal. Because see the basic expectation is OA dash upon OA has to be my ratio K. And so if you think of them as directed distances, then this makes perfect sense. Because now OA and OA dash are in opposite directions. So one will be positive, one will be negative. And so this will be exactly -1. So that is why if I take O as the center of, basically you can think of this as reflection through O, right? Reflection through a point. So in the same way, BO can be extended to B dash. So you are going to get this kind of parallelograms and C will go to C dash. So your original triangle has now become this triangle. Okay. So this is also homothety with the negative ratio. But important observation that although this looks like reflection, this is distinctly different from reflection in a line because what reflection in a line does is changes the order of the points. Like here ABC are anti-clockwise, right? ABC anti-clockwise. And here also A dash, B dash, C dash are anti-clockwise only. So this is not what a mirror would do. If I take a mirror image of ABC, then the A1, B1, C1 change, they become clockwise. So this is not reflection in a mirror. This is more like reflection in a point. Okay. So pay attention to the difference. So in fact, if you think about it, can you convince yourself that homothety with ratio -1 is the same as rotation with 180-degree angle? If I take O as my center of rotation, right? We know how to do rotation. So imagine that I take O as my center of rotation and rotate the triangle ABC. If I keep rotating, and I rotate it through full 180 degrees, do you see that it will be the same picture? Because A will rotate and go to A dash, B will go to B dash, C will go to C dash. So, particularly when the ratio is -1, the same operation can be also thought of as a rotation with 180-degree angle. Okay, both of them will give you the same result. But of course, this is with a special case of k equal to -1 because there the new triangle and the original triangle are congruent. But I could draw a diagram where k is negative but not -1. Like suppose I try to draw a diagram of k is equal to -2. So now what will happen with k is equal to -2? What do you think will happen now? So can I draw the diagram like this? If I extend each line, again I'm going to go to the other direction because I want OA dash upon OA. So I would like OA dash upon OA to be equal to -2. So I need OA dash and OA to be of opposite signs. But OA dash has to be 2 times OA, right? So basically, uh, so I'm taking OA dash twice as far as A, right? So OA dash is 2 times far away. OB will also become OB dash, which is 2 times far away, right? And OC will also become OC dash. So you see, because OC is the largest segment, so OC dash is twice that large, so it is going really far away. And so you see, again, the triangle is getting inverted through O, but inverted and enlarged both at the same time. So this is doing, because you can think of this as -1 into 2, right? So it is a combination of two homothety. First, the -1 will flip the triangle, and then the 2 will magnify the triangle. So you can combine homotheties that way. So already we are starting to think of how you can combine two homothety. Like two homotheties from the same point can be combined by just multiplying the ratios together. Just as two rotations from the same point can be thought of by adding the angles. So we are already seeing that possibility here that homotheties can be combined in a very natural way by just multiplying the ratios together. So can anybody tell me what will be the inverse of this? Suppose I have to go from ABC to A dash B dash C dash, I have to do homothety of ratio -2. If I have to go back to ABC, what will be the ratio I have to apply?
-1/2.
Yes, -1/2, right? Because in terms of geometry, what I need to do, I need to take the inverse, like invert the triangle and shrink it by half, right? So it is -1 into half, or in other words, -1/2. And you see, so these are nicely reciprocal. So in other words, whenever you like homothety of any ratio k, non-zero k, and the ratio 1 by k, right? If I combine homothety of k and 1 by k together, it is equivalent to doing homothety of ratio 1, which is the same as doing nothing. So we are going to come back to the original object every time. Okay. Okay. So I hope everybody has understood this, how negative ratio homothety works. Okay. And so we can talk about a few more properties of homothety, but before that, so in the context of triangle properties that you already studied, right? I hope all of you have studied things like orthocenter, 9-point circle. Have you studied all those things? So in that, do you see this homothety being applied? Can you relate this homothety idea there? Like for example, take the case of medians, right? We all know medians are concurrent, and we get the centroid, right? So the centroid is where the medians intersect. And we also know that the centroid divides the each median in the ratio 2:1, right? So if I want to call the centers of the midpoint of the three sides as A1, B1, C1. So we all know that G divides each median in the ratio 2:1, right? So now can you think of restating this in the form of homothety? What will you say in terms of homothety?
Excuse me, sir.
Yes.
Sorry to disturb, but can you just scroll up to the beginning? I just want to look at it.
Okay. Right to the start, or where do you want?
Yes, sir. It's the start.
Okay. Okay. Yeah. Yeah. I mean, just to quickly recap, in case you joined late, that I just started by showing what are the transformations we have studied so far. So we talked about translation, rotation, reflection, and I just mentioned that what is the input required to define each transformation. Like for translation, you need to know the vector. For rotation, you need to know the center of the rotation and the angle. For the reflection, you need to know the line. And then what is the corresponding operation in terms of the complex coordinate, which will achieve the same output. And so then we started to discuss, and one important operation there is called conjugation, which you can read more about if you don't know what is a conjugation. And then I started to discuss about similarity transforms. So the first transformation we are doing right now is spiral, sorry, just homothety.
Sir, homothety
So
requires a given point as well, right?
homothety, yes. So homothety, you need to know the point, the center of the homothety and the ratio, right? So these
Okay.
two are the required data to define the homothety completely.
Okay, got it. Thank you.
Okay. So how will you express this fact that G divides each medium in the ratio 2 is to 1? So can you tell me what is the relation of A and A1 in terms of homothety? Because can I write that A1G upon AG is equal to minus half, taking directed distances? Does this make sense? That A1G will be, in terms of magnitude, A1G is half of AG, but the sign is reversed. So that is why I have to write it as minus half. So therefore, can I say that A1 is the image, and this is an important because this is how you're supposed to write. If you want to write a full sentence, that this is the operation I'm applying, and this is the result. So image of A under homothety around G with ratio minus half. Okay, so this construction of the sentence is very important. That I'm stating what is the operation being applied. And so you see the clear separation that the definition of the operation doesn't have any mention of what is the object on which I'm doing the operation. So homothety around G is a general operation you can apply on any point in the plane. And then I'm saying that if A is the input, then A1 is the output. So these three objects have to be clearly defined. If you're anytime you have to write homothety or any transformation in exam, the clarity is very important. Okay, so does everybody agree that this is a good way of describing that A and A1 are related under homothety of this operation? What about B and B1? It will be the same relation, right? B and B1. So again, instead of A1, I could say B1 is everything else is the same. And very importantly, the homothety itself is also the same. So whatever operation is going to take A into A1, that is homothety around point G with ratio minus half. It is the same operation that is going to relate B1 and B and C1 and C. So it is not like I need three different transformations. The same transformation is going to simultaneously take A to A1, B to B1, and C to C1. And so this is one more proof you can say of why the triangle A1, B1, C1 is congruent, or sorry, similar to the original and with ratio half. So I mean, you already know this maybe from basic geometry that A1, C1, B1, C1 triangle is similar to ABC with ratio half, like by midpoint theorem, you can get it. But by homothety, I'm giving you one more proof of this, that why the ratio is half, why are these two triangles similar? Okay, does everybody uh, follow this proof or rather explanation?
Yes.
So, as a consequence of this, see, transformations have one very nice property that when one object becomes another object, it carries all of its properties together. Like everything related to the first object also becomes into the second object. So what do I mean by that? Just to illustrate one small case. Suppose I have triangle ABC over here and I apply very simple apply. Let's say just translate. Okay, I'm going to translate triangle ABC to a new position. Okay, A1, B1, C1. Okay, so I have translated the whole object like this. Suppose I look at some particular object within ABC, like let us say I drop the altitude, okay? So let us say the foot of the altitude is D. And here also I have dropped the foot of the altitude is D1. So do you see that if I apply the same transformation to D, so D is going to go to D1 under the same operation. So whatever is the connection of A to A1, the same is going to be the connection of D to D1. And the same is true for every object in ABC. So if I take the circumcenter of ABC and I apply the same transformation to O is going to go to the circumcenter of my new triangle, and so on and so forth. So everything about the first triangle is nicely carried over to the second triangle. And this is true for all the transformations we have seen. That it is true for translation, rotation, reflection, for homothety also. Like suppose I decide to let me not call this point O, or let it be O. I mean I can choose some different point O, or K. Okay, okay. R. Okay, R. So suppose R is the center of homothety, and I apply homothety to triangle ABC, and let us say ratio 2:1. So under that ratio homothety, the triangle will become a larger triangle like this, maybe something like this, right? So the triangle has increased in size, but do you see that the circumcenter of the original triangle, if I apply the same homothety to that, so O will go to new position O2, let's say, right? The O2 is going to be the circumcenter of my new larger triangle. So the circumcenter has moved, the circumcircle has also moved and increased in size. So circumcircle will be twice the size. Everything gets nicely translated. This is one of the most important properties of transformation, because of which transformation becomes a very useful tool. So if we imagine that here, so triangle ABC has a circumcircle. So what do you think will happen to that circumcircle under this particular homothety? Which homothety? The one which you are referred to here. This homothety around point G with ratio minus half. What will the circumcircle of ABC become? So if I draw the circumcircle of triangle ABC, so maybe the if O is the center of that circle, okay, not a very good circle. Let me draw in. So if this is the circumcircle. Under the same homothety, you see the circumcircle of ABC will become the circumcircle of A1 B1 C1. So if I draw the circumcircle of A1 B1 C1, maybe something like this. And do you know any other name for this circle?
9 point circle.
It is a 9-point circle, right? Because three of the 9 points are the centers of the mid, or the midpoints of the three sides. So in other words, what are we saying? That uh, we have observed something very interesting, that just as triangle ABC is the image of, so I could write it like this here, that triangle A1 B1 C1 is the image of the original triangle under the same homothety. So let me develop a shortcut. Writing this whole phrase every time is a lot of tedious work. So let me just write HOM for homothety the center of the homothety and the ratio, right? We had developed a similar short form for all the other operations we did so far. So let us use that. So under this particular operation, triangle ABC becomes A1, B1, C1. Therefore, the circumcircle, again, actually, I don't need to write circumcircle. We have this notation, circle ABC, right? Circle A1, B1, C1 is the image of circle ABC under the same operation. Okay. And again, like suppose you want to write it even shorter way. So again, just to illustrate that, you could write this operation in two, three different ways. So this is like the complete English sentence. You could shorten it by just drawing the original object, draw an arrow. On the arrow, you describe the operation you're talking about, and then here you write the final object. So this is also conveying the same information that the original object is ABC. This is the transformation you're applying, and this is the final object. Or another way is the function notation, right? So in terms of function, you could write that. So this is, you can think of this as a function applied to A will give you A1, and similarly for B1 and C1. So like two, three different ways of writing the same information, whatever is comfortable or whatever is suitable for that particular description. Okay. And so what we are saying here is in this expression, this triangle evolution, circle evolution is nothing but a 9-point circle, right? So basically, if I take the circumcircle of ABC, fine, you're right, and I apply this homothety, I'm going to get a 9-point circle of triangle ABC. Okay. And under that operation, what is going to happen to the center? So O is going to go to the center of the 9-point circle, right? And that is also be related to the same ratio. Like if I denote the center of my 9-point circle as N, which is typically the letter we use. So in this diagram, what are we getting that Ng upon Og will be also minus half. In other words, G is dividing the, or rather I would say, yeah, G is dividing the segment OL in the ratio 2:1. Okay. So G divides segment ON in the ratio 2:1 as Ng upon Og is equal to minus half. And actually, you can use this as a starting point to get one more proof of the fact. See, here we are not proved that this is the 9-point circle. So far, what we know, this is just the circumcircle of the points A1, B1, C1. What is the proof that this is also the 9-point circle? So you must be doing a different proof through angle chasing. But now I'm going to suggest you can prove this using transformations also. Because in this diagram itself, if you think about it, what will happen is OA1, if you look at OA1, right? Okay. So O goes to N under this operation. A1 will also go to new point, right? So let me denote the point where A1 goes like something like A2, right? So A2 is the image of A1 under the same transformation. And so what will happen? You are going to get similar triangles, right? So this OA1 is going to be parallel to this one, right? And half. Actually, I think my diagram is not very good. I know A2 does not go there. A2 is actually going to lie. Let me magnify the diagram for the purposes of this. So actually our N will be somewhere over here. Okay, so N is such that OG upon GN is equal to minus half. So maybe I'll ask you this question, that where do you think the image of A1 will go? What will be the image of point A? Because if we denote the full distance, let us, because we typically denote the length of the median as MA, right? So MA is the length of the full median. Then out of that, what is the length of GA1? GA1 will be one third of the median, right? Because G is dividing the median in the ratio 2 is to 1. So GA1 has to be one third of the median. And now through G, if I apply the homothety again, and wherever I get A2, right? So wherever that A2 lies after the transformation, we know that A2G upon GA1, or rather GA2 upon GA1, has to be the ratio minus half. So can I compute GA2? How much is GA2 going to be? Minus GA1 by 2. So it is going to be minus MA by 6. Right. So I don't know. Looks like a weird expression, minus MA by 6. Is it useful in any way? Where do you think this A2 is going to lie? Okay. So temporarily ignoring the sign, just keeping the magnitude. So I'm going to drop this minus sign. We're just looking at the signed, unsigned value. So GA2 segment is of length MA by 6, and this is MA by 3. So how much is A1, A2 coming to be?
So it will be MA by 2.
You see it is MA by 2, MA by 3 plus MA by 6, which is MA by 2. So in other words, where is A2?
So it will be on B1, C1.
A2 is the midpoint of the median, right?
Mm.
So it is going to be this intersection point. So interesting that under the same homothety, which takes A to A1, it takes A1 to A2. And there is one more reason why that was supposed to happen, because G is the center of A1, B1, C1 also, right? So just as G is the center of ABC, that is why each point, each vertex becomes the midpoint of the opposite side. The same is applicable for triangle A1, B1, C1. Here, each vertex A1 is going to become the midpoint of the opposite side, which is B1, C1. So A1 goes to A2. And you see, in fact, so there is a what you can say infinite repeating pattern here, that each triangle is going to become the triangle of its midpoints, and the triangle inside that is going to become the triangle of that midpoints. So it is like an infinite tunnel. Yeah, you keep on getting, like, here this is the new triangle. If you take the apply the same operation again, it is going to become this triangle and this triangle and this triangle. So it's going to keep going like that, smaller and smaller triangles. Okay. So so the whole point of doing all of this was to prove that. So let me just simplify the diagram a little bit to give the important information. So what I'm suggesting is that if you take triangle ABC, let A1 be the midpoint of one side. So let O be the circumcenter, and okay. So right now I'm going to say N is the center of circle A1 B1 C1. I'm calling it N because I know it is going to be the 9-point center, but we don't know that yet. I want like to prove that it is the 9-point center. That is why I'm just calling it the center of A1 B1 C1 circle. Okay. But based on what we just proved, that under that homothety, we know that the homothety around G with ratio minus half will take O to the N, and it is going to take A1 to A2. Same homothety is going to take A1 to A2. What is A2? A2 is the midpoint of B1 C1, or it is the midpoint of the median. Both is the same, right? So therefore, what I'm going to observe is that NA2 is parallel to OA1, correct? And A2 is the midpoint of AA1. Okay. So if I extend OA, not OA, extend ON to point H such that ON is equal to NH, right? So if I extend ON to new point H such that N is the midpoint of OH. Okay. So then what we're going to get is that ONH is a system of three points such that one is the midpoint of the other, right? And so do you know this property that if you have 3 points such that one is the midpoint of the other and you draw parallel lines, right? Let us say you draw parallel lines through all the 3 points. See, any combination of intersection on these three lines always going to have the same relation. They are always going to be the center point to the midpoint of the other two, right? No matter which transversal you draw on those three parallel lines, you are always going to get the same configuration. So you see something similar is going to happen here now because O and H are that system. Like N is the midpoint of OH by construction. And in here, we already have two parallel lines, right? These are parallel lines. So which is going to be the third parallel line? And note that A2 is already the midpoint of AA1. So what is going to happen? Do you see that we are going to be forced to conclude that AH is also parallel to this OA1? Okay. So I'll skip the details here, but I hope you can work it out that you can prove that. I'll write we can prove that AH is parallel to OA1 because why? H and O are collinear with HN is equal to NO. Then similarly A2, A1 are also collinear with A2 is equal to A2, A1. So basically you have the diagram is something like this that you have one set of midpoints which is given, okay, and another set of midpoints such that out of these, if I join two of them, right? So this is and these two are parallel. This is given. So therefore you can conclude that the third one also has to be parallel. That is what we are using here basically. So why this is true? I'll do it as exercise for you. But therefore AH is parallel to OA1. Therefore AH is actually perpendicular to the base. And therefore in the same way what you get is that H has to be the orthocenter. So I don't know. Those who have studied 9-point circle, is your proof somewhat similar to this? You may have done a similar thing to show that OGH are collinear and the 9-point circle. Basic setup is something like this only, right? But I'm just showing it how the same thing can be also described in terms of geometric transformations. Okay, and from here the remaining part follows very naturally. That why? So far we have only shown that H is the orthocenter, but what about the 9-point circle? So 9-point circle, we have already shown that A1, B1, C1, which are the midpoints of the three sides, are that circumcircle which has center N, right? Why should that also pass through the midpoints or the foot of the altitudes? And all those things we are not proved. But I think those readily follow from this diagram because what will happen if I take the foot, let us take 1 foot of the altitude D. Okay. So here you clearly see that N is going to be equidistant from A1 and D because of the same reason that you have these three parallel lines right? So, or rather, with some more working, you can show that ND is equal to NA1. Okay. If you show that ND is equal to NA1, then that is the radius of your 9-point circle. So D has to lie on the 9 point on that particular circle. So that will take care of one part. And the second part is what about the midpoint of AH? So if I take the midpoint of AH as X, right? Then I don't see the exact calculation here, but somehow I think we can get AH is 2 times OA1, which is again the property we know. So we can, once we prove that, then it will follow, because then what will happen is that X, it is going to form a parallelogram, right? This, if we prove that AH is twice 2 times OA1, then what we're going to get is each part, right? This part is going to form a parallelogram like this, and therefore from there also we'll get the same property. So because this is a parallelogram, then we know midpoints, the diagonals bisect each other, and so OH is one diagonal and XA1 is the other diagonal. So they are going to meet at the 9-point center, and then N is going to be the midpoint of XA1. So I think we just need to calculate this and get the answer. Okay, but I'll leave that as another exercise for you. Okay, so basically, this homothety is very deeply embedded in this basic theory which all of us have studied. And not only this, the further implication of this is that, so we already said that 9-point circle, so 9-point circle is the image of the circle under what is the homothety? Around the centroid with ratio minus half. But there is one more way to go from the circumcircle to 9-point circle. The 9-point circle is also the image of homothety of ABC under another homothety, which is around the orthocenter with ratio half. Okay, so let me explain this point in a little more detail. So actually, what happens whenever you have any two circles, right? Any two circles, it is natural to ask the question that can I take one circle to another circle through some transformation? So clearly, if the circles are not of the same size, then it cannot be a congruence transformation. So it has to be some kind of similarity transformation. So homothety is the transformation that we can think about. That can I apply homothety to convert one circle into another circle? So the answer is yes. You can do that. And to find the center of homothety, it is enough to draw the common tangents, right? So if I join these two, in fact, there are so many ways to do it that you can probably just take any two parallel radii. So if I take two parallel radii and if I join these 2 points, right, wherever they intersect the line of centers, so I can choose O as the center of homothety, and suppose I call this radius R1 and radius R2. Okay, then I can see that, or rather, I would say I'll leave it as a proof for you to prove that the first circle gamma 1, if I apply homothety around point O and the ratio has to be R2 upon R1, right? Then the first circle will become the second circle. And under that, all the points, so this, the center of the first circle will become the center of the second circle. All the corresponding points will also go. So P over here will become P1 will become P2. So you can apply homothety around O to take the first circle into the second circle. And in particular, what we'll observe, because O1 also goes to O2 under the same operation, right? So therefore, I can write the ratio of the distance O2O upon O1O will be that R2 upon R. In other words, O divides the segment O1, O2 externally in the ratio R1 is to R2. Okay. So for example, in this diagram, roughly speaking, it looks like the second circle is two times the first circle, right? So the ratio of division is 1 is to 2. So you'll see that O1 O upon O2 is roughly half, right? Ignoring the sign for now. So but the natural question one can ask is, this is the external point, but any line segment, you always have an internal and external point of division, right? There will be a point internally also, which also divides O1 O2 in the same ratio, R1 is to R2. And so that point can be obtained by drawing the internal common tangents. So if I draw the external common tangents, I am going to get O. But if I draw the internal common tangents, okay, I may get a different point. So what about this point? Can this point O dash also be the center of homothety to take one circle into another circle? So the answer is yes. So only difference is that if I were to choose O dash as my center, then it is like a mirror image, right? So it has to be inverted. It is not the normal positive ratio, it has to be negative ratio. So here then what will happen is that O dash, so the first circle gamma 1 goes to the second circle gamma 2 under a different homothety. Center is O dash and the ratio is now minus R2 upon R. But everything else remains the same. So in general, so any two circles are related by two homothety operations. Okay. So there are two kinds of homothety that can be applied to take one circle into another circle. So the first operation is center is external point of what your ratio R2 is to R1. And here the ratio is positive. And the second point is the internal point of division of the same ratio. And now the ratio is negative. Okay, I'll just take a pause here because I've covered a lot of theory in a short time. So, any doubts, anything that you want me to clarify? That why two circles can be converted to each other through homothety like this is the important point. Okay, maybe we can just draw a few diagrams on GeoGebra to make this clearer. So, what can we do? Let us take any two circles. Okay. Okay. So I'm interested to find that special point on this line such that with that point I can apply homothety to convert one circle into the other circle. So based on the what we have studied, we can directly consider the point on this line which divides AC internally and externally in the ratio of the radii. So uh, or alternately, what I have suggested is that we can do this way. I can take any point on the first circle. So I've taken E as any point on this circle. Okay. And I'll take a parallel line to that through the point C. So, yes. Okay. So you see it is intersecting my circle at a new point F. And so if I move my point E, the F also moves. But throughout, what you'll observe is that if I join EF, right, and if I mark this point as O, okay, so even if I change my point E, you see O does not change. And I mean, this is easy to show using basic similarity. There is nothing, basically, you can show that AO upon OC is the same as R1 upon R2, right? So therefore, obviously, O will not change. But the important thing is now O can be the center of homothety to convert this circle, the first circle, into the second circle. Okay. So this was the external center of homothety. What about the internal center? To obtain that, I just have to take the diametrically opposite point. So here I got the point F, but there is one more point over here, G. So I could consider the relation of E with G. So if I join it this way, again you are going to get parallel lines. EA and CJ are parallel. So again, if I take this point, I'm going to get similar triangles, and you can see that AH upon HC has to be equal to the ratio of R1 upon R2. So again, if you see, if I move the diagram, H is also not changed. So both O and H are fixed points, and they are going to be the centers of the homothety, which will convert the circle, first circle, into second circle. But only difference is that the signs are opposite, right? The if you take O as the center, it is a positive ratio. So AE becomes CF directly without changing direction. But if you take H as the center, then it is a negative ratio. So AE becomes CD. So the direction is flipping, right? AE, if AE is pointing upwards, then CD is pointing downwards. Okay. So this is true for any two circles. If I move this circle anyhow, it is going to be true. So it is going to be true for 9-point circle and circumcircle also. So for 9-point circle and circumcircle also, there will going to be some two special points which will divide the line of centers internally and externally in the ratio of the radii. But in our case, it happens to be two very special points. They happen to be the centroid on the orthocenter, right? So if I delete this diagram and construct a triangle ABC, okay, and let us say for now, I did not know that, oh, I'm going to get centroid. So let me just draw the circle, like let it be a surprise for us that this is what is going to happen. Although you already know, so it is not going to be that surprising, but let me take the midpoints of the three sides. Okay. And let me draw the circumcircle of these 3 points. Okay. So I can ask the same question as before, that what is the center of homothety to convert one circle into another circle? So again, as before, what I can take is I'll take the centers of the two circles, G and H. Oh, interesting. So they are, I would like to call it something different. We have G and H, but they are not these points. Okay, so typically we denote the circumcenter by O and this point by N. So same as before, if I decide that if I want to locate what is that point of homothety, or center of homothety, so I'll just take any random point on the circumcircle, let us say. Why is it calling it G every time? Okay, so what I'm going to do is, so OP is my radius, like variable radius, and parallel to OP, if I draw a radius through N, right? So if I draw a parallel line to this through my point N, right? And so if I look at again G and H, it is just because that the letter is coming in that sequence, right? So let me call that P1 and P2. Okay. So my expectation is that if I join P and P1, right? And where should I join it? I should join the centers of my two circles. So that is fixed. So this ON is the what we call the Euler line. So notice where this P1 is intersecting this ON. Okay. Again, not G. We know this is going to be H. Maybe I should have considered the other point first. So now if you observe again what we expect to happen if I move the point P, H is not changing, right? H will always remain fixed because H is the point which is dividing ON in the ratio 2 is to 1 or maybe yeah 2 is to 1, 1 is to 2, whatever. And so what based on what you have shown in the through the geometry is that H is the orthocenter and it appears that way, right? In the diagram also it looks pretty close to the orthocenter. So that therefore orthocenter is one center of homothety. And which is this? This is the positive ratio or the negative ratio? This is the positive ratio because here the segments, the OP, if I denoted the vector, OP and NP1, they are both similarly oriented. So therefore, H is the positive center of homothety, where the ratio is positive. But similarly, I'm going to get a negative center of homothety by instead of taking P1, if I take P2 and join P and P2, right? So where this P and P2 meet my, so now this is going to do the yes, very good. I would wanted the letter G and I got me the letter G. So this point G is going to be the internal center of homothety. Again, it is not going to change if even if I move the point P. Okay. So we are just recreating the standard OGNS Euler line. I guess we all know this theory. So there's nothing new here. I'm just showing that how all of this can be also arrived through transformation logic. Okay. So G is the centroid. So G is the you see there is so many properties overlapping on G. G has so many nice properties. So G is the point where all the medians intersect. G is also the center of homothety with ratio minus half, which will take the circumcircle to the 9-point circle or vice versa. And G is also on the Euler line and everything is happening. So both point G and point H have lots of special properties. Okay. So yeah, so observe these things that how and as a result of this homothety, so many things are going to follow naturally as a consequence. Like for example, if I take this point P at my vertex A, what is going to happen? Because of this homothety, the image of let us say H as the center of my homothety with ratio plus half. Okay. So under ratio plus half, this point P is going to go to P1, right? Because it is just going to be the midpoint. So therefore, obviously, the midpoint of AH is going to be on the 9-point circle because it is just the image of that homothety. And in the same way, this point P2, which at this particular moment is the midpoint of BC, is also going to be on that circle because again it is the image of that homothety. So, in the one diagram, suddenly all the entire 9-point circle theorem is getting proved in just one diagram because of this homothety. Not only that, one other property which you may already know is that if I take the point P over here, right, if I extend the altitude AH, let it meet the circle again at a new point P, then you may already be knowing that P1 is the midpoint of H and that point of intersection. So you see one more reason why that is going to be true. It is true because again P is a point on the circumcircle and if I apply homothety, I know that P is going to go to the 9-point center, the circle, the point on the 9-point circle. So which is that foot of the altitude. So you see so many things get connected if you just take some special position. Another special position to consider is that if this point P1 goes to D, observe what happens. So at this point, notice how the diagram is looking like. So P1 is at the midpoint of BC. So if I extend HP1, it is meeting my circumcircle again at a new point P. What can you say about this point P? Do you see anything interesting about this point P? What should this point P go to? Where should it lie? When this P1 is at N, So if you think about it, in the smaller circle, in the 9-point circle, what is the relation of P1 and P2? P1 and P2 are always going to be diametrically opposite points. Why? Because that is the construction, right? This line which you have drawn, which is parallel to the this radius, it is always going to make P1 and P2 diametrically opposite. But especially when P1 coincides with D, now the diametrically opposite point of P1 in the 9-point circle we know is the midpoint of AH, right? So at this particular position, P2 is the midpoint of AH. So therefore, what is going to happen? Anybody can suggest what is the position of point P? What is special about the point P in this particular configuration?
Is it diametrically opposite to A?
Yes, correct. It has to be diametrically opposite to A. And why? Because that is what homothety does, right? See, P1, P2 are diametrically opposite, and I apply the homothety of ratio 2 is to 1, which is going to take P1 to P and P2 to A. So therefore, P and A have to be diametrically opposite. So you see, we are getting one new property which I don't know you may have not realized before, but this is true that in a diagram, in a standard configuration, just going back to my tablet for a minute. So what the diagram is suggesting is that, so and now it is up to you to prove this using pure geometry if you want. But if you take the orthocenter, okay, extend the orthocenter through the midpoint of the side, okay, and let it meet the circumcircle of ABC again at a new point A, A2 maybe. Then this A2 and A are diametrically opposite points. Okay, maybe you already know how to prove this using pure geometry, but again, this is a nice corollary of what we are doing here. Okay, and so on and so forth. They are going to get so many properties like that because of their transformation connection. Okay, and so this is just one application of homothety. I'm going to suggest one more application to you, and you have to think about this more. Like think of the in-circle, X-circle configuration. There also you are going to have so many different kinds of homothety because obviously the in-circle with the right ratio can be transformed and made it like converted into the X circle, right? Applying the homothety, so if the ratio, the radius is R and R1, so if you take A as the center of homothety, R is the first in circle is going to become the X circle. So again, you can ask the question, what is there one more point of homothety, like center of homothety, what are the properties, and so many things you can ask, okay? And you can ask the question not for in circle to X circle, but between two X circles. Like what is the connection of the first X circle with the second X circle? What is the homothety being applied there? What are the two? What is the internal point of homothety? What is the external point of homothety? And so on and so forth. There are many questions you can ask and answer over there, and that will lead to some more properties. Okay, so think about all of these possibilities. Okay, so uh, we don't have a lot of time, so let me come back to this table briefly. So now, based on whatever complex numbers you studied so far, can you tell me that what should I fill up here? If Z is my original complex number, right? The original point has the complex number Z, and I'm going to apply homothety with the center as my origin and a ratio K. What is the new point going to be?
A times Z.
Yes, K times Z, correct. And the reason is very simple because when you multiply a complex number with a real number, it is basically multiplying the real and imaginary parts both with that ratio K, right? So you are going to, if I were to show this in a diagram, it is simply that if this is my original point Z, which has complex coordinate x plus iy, right? And whatever is that ratio k, let us say for diagram k is 2. So in other words, I'm going to, if O is my center of homothety, then P is going to go to a new position P dash, such that OP dash upon OP is 2, right? So when will this be true? If I multiply both the x and y coordinate with the same ratio. So therefore, if I point this new point z dash has to be kx plus I times ky. Or in other words, if I take k common, k times z. Okay. So therefore, homothety is just multiplying with a real constant. And you will see that this is true for all values of k. So if k is positive, this is true. Even if k is negative, it will be the same thing. So if you take the case of k is equal to -1, then z will become minus z, right? So if x plus iy, which is the point x comma y, then what will be the minus of that? It will go nicely in this quadrant, right? You see that? So the point P dash over here, which has the coordinate minus x comma minus y, or the in terms of complex number, it will be minus z, right? So this expression is going to work for all values of k, positive, negative, even zero. If I put k equal to zero, then my entire plane is going to collapse to the origin, right? All the points of the entire plane are going to suddenly come to the origin. So that is not a very interesting operation, obviously, but yeah, technically it is also homothetic. Okay. And so see, every time we add an operation, we also have to ask the question that what is the combination of this operation with some other operation. So first question which we have kind of already answered, although you have not proved it, is that combining two homotheties. So again, we can make case wise. So case one, around same center. So this is the more trivial case, right? Suppose O is the center for both operations. So the operation one is homothety around center O with ratio K1, and second operation is homothety with the same center and operation K2. So what will the combination of these two be? It will be the same as applying homothety of ratio K1 into K2, right? It is like you first magnify the object with ratio K1 and then again that with K2. The result will be as if you apply the K1 into K2 operation together, right? So again, if you have to write this in the multiple ways to denote this, right? One, you can do it in arrow notation, like the original object or a original point with the first operation becomes A1 and the second operation becomes A2, or directly with one operation. And you see how in terms of complex number, this is obvious because we know multiplication in complex numbers. I mean, I don't know, we know, but we can prove it that multiplication in complex numbers can be is associative. So you see that if you know k1 times z into k2 is the same as k2 k1 times z. So this is exactly this algebraic fact is being denoted through the geometry of homothety. It is nothing different. Oh, sorry, k2 k1. Another algebraic fact is that order does not matter, right? If you are applying homothety around the same center, you can reverse the order. So you first do the homothety of K1 and then K2, or somebody wants to do the homothety of K2 first, then K1. You are going to get the same answer because the K1 K2 is the same as K2 K1. So it is commutative also. So all of this is for homothety around the same center. But what about a different center? So case 2. Suppose first operation is homothety around center O1 with ratio K1 and second operation is homothety around its different center and different ratio. So now, can we combine these also? So just to take an example, let us say I first apply homothety around this point with ratio 2 is to 1. Okay. So let us say the first ratio is 2. Just drawing the diagram very roughly. Okay. And then I take a different point, and now let us say the ratio is 1 by 3. So in the diagram, it looks very convincing that there has to be some way of going from the original object directly to the last object. And we clearly see that the ratio of homothety is going to be just the product, right? So the combined ratio is simply going to be 2 into 1 by 3. But where the center is going to lie,
So what center have you taken for the second homothety?
it's some different point, any random point.
Okay.
So if O1 is the first center, O2 is the second center. Looking at the diagram, it looks very possible that the combination of these two will be a homothety around some third point, right? Some third point, if I call it O, such that directly from the original triangle to this new purple triangle with the ratio 2 upon 3, I can get there in one step directly. So that looks possible from the diagram, but we need to prove it. And not only that, if we can locate this point O very nicely, that will be very nice, right? Can we locate this point O very nicely? What do you think? Can the point O be located anywhere in the plane, or it has to be some special point? Like one thing should be obvious. If I join the line O1, O2, is there any special preference that O has to be on one side of this line or other side of this line? That will break the symmetry, right? So what is the only possibility? You see, only possibility is O has to lie on that line only. Otherwise, the symmetry will break. If the center O lies on one side, then somebody could just take the mirror image of my whole diagram and they will get another position of the O. But you cannot have two different positions like that. Should have one position. So therefore, the only conclusion is that this center of combined homothety has to lie on the line O1 or 2 only. Somewhere. We don't know where. Okay, that is the first observation. And not only that, you can find the position of that O very nicely.
I think we should divide O1, O2 in the ratio of the final homothety. So it's 2 by 3. So
Ah.
maybe we should take O1 upon if O
Yes.
is 2 O2 upon O. Oh, sorry. O1 O upon O2 O is equal to 2 by 3.
Yes, correct. Uh, Not exactly. You're almost correct. I would say the reverse order, and I'll explain the logic why. Let me just draw the diagram again here. See, the important thing is that the first transformation, right? The homothety of around O1 with ratio K1. Let me just call it terms of K1, right? So homothety around O1 with this ratio is going to transform the whole plane. So there in the above example, I took one triangle, but I could take any object in the plane, right? I could take any point in the plane and I apply this first homothety. And let us say it goes to new point P1. And to that same point P1, around O2, I'm going to apply the homothety, which is going to get new point P2. And so my claim is that this P and P2 have to be related through homothety around the new point O. So to locate this point O, I can free to choose this point P anywhere in the plane. So which point should I choose to simplify my diagram? Which is that special point for which computing this chain of steps, like going from P to P1, P to P2, P1 to P2, can be simplified.
So given any ratio,
Yes, given any ratio. Why don't I take the point P at O1 itself? Who stops me from doing that? If I take my point P at O1 only, then where will P1 go? Where will P1 go?
it will be over itself, right?
Yeah, it will be 1 itself, right? Because the distance O1 is 0. So 0 into anything will be 0. So you see the first step of this chain is completely eliminated. So do you see that basically, and if I start to think again that at O1, so O1 is my point P, I have to first apply the first homothety of ratio K1. So I am going to get P1 at the same point. And now at the same point, I'm going to apply homothety with O2. So now that will change. So let us say that goes to new position, like K2. Okay, so let P2 is over here. So here now the equation is simply O2 P2 upon O2 O1 is the ratio K2. And now on this line, I have to look at the point O such that around point O, the original point P, right? OP upon OP2 is supposed to be K1 into K2. But instead of writing P here, I can replace P by O1, right? So, and I could write this as simply O1 upon OP2 is K1 into K2. So like that, I can do all of my calculation on this line itself to obtain the point O. I don't need to look anywhere else.
So we don't know
Okay.
P2, right?
We don't know P2, but we can locate P2 from O1, right? I can apply the homothety to O1 to get P2.
Okay.
So first I'll dilate O1 to get P2, and then from this I can calculate. Or actually, I'll suggest you can simplify this expression and get directly the position of O in terms of simply the distance. So if I give you the distance O1, O2, so just three variables, the distance between the 2 points and the two ratios of homothety. Using these three as the input, you can locate the coordinate of this point O. Okay, it is a simple calculation which you can try. Okay, but I've not given the full proof of this. That what is the proof that just because O1, O2 are related in that way, why should the entire homothety operation also be related in the same way? So that is not, I have not given the proof here, but you can spend some time offline to think about this, that why it is going to be the case. But at least I hope to convince you looking at a diagram that a combination of two homothety is another homothety. And this is unlike previous case where we have to do some, special case work. I think this is always going to be true. I think only condition is that we are going to take non-zero ratios always. We don't want to deal with zero ratios. Okay, so as long as the ratios are non-zero, you can combine two homothety to become one more homothety. Okay, but then I'll leave it as exercise for you to think of what about other operations. Like if you combine homothety with the translation, or what about homothety with the rotation? What about homothety with the reflection? So all these three we need to think about. And well, you may have some intuition, you may do some experiments, but whatever is the conclusion, we have to prove it finally. Okay. But in the interest of time, I will not go through these details, but I'll encourage you to think about all of these questions.
So in all of these questions, it cannot be any congruence transform for sure. So it must be similarity
Yes.
transform, that is homothety. Then we have to
Yes.
find some other, it will be on some other point.
Yes, correct. So the what you're saying is correct, that because there is homothety involved, you can never have only congruence transformation to describe this. But sometimes you cannot simplify this also. Like for example, what you will realize is that these two operations are going to remain as it is. Like homothety and rotation together, there is going to be one more row we are going to add called spiral homothety. So that is a combination of a homothety and a rotation. So that is the last transformation we need to do for now. Okay. So In this, there will be one more row added called spiral homothety. Actually, I was planning to cover it today, but may not have the time. So spiral homothety is the new homothety, which is a combination of rotation plus reflection. Okay. Sorry, rotation plus normal homothety. Okay, so we are going to study this next time. So this is going to be a very powerful operation. Spiral homothety is going to unlock lots of possibilities. With, of course, it is a powerful operation, so it has lots of properties, lot of things that we need to understand very well. I think we need to understand complex numbers in a very proper way to appreciate the spiral homothety. But let me state the problem, which I at the beginning I said, right? I would like to solve one particular question. Why I am doing all of this theory is to solve that one particular question. So let me go to that question. This is a very interesting question that we can try to solve with all this knowledge. So again, to recap, last time we did one question was that given two lines and a point, right? Remember this question that lines are given and a point is given. Construct an equilateral triangle. PQR, where P is fixed, right? P is given and Q lies on the first line and R lies on the second line. So we had done this with rotation very nicely. We finished the question very nicely with rotation. A slightly different question can be asked that in a triangle, so triangle ABC is given or fixed, right? So triangle ABC is fixed. Now inside this triangle, I want to construct an equilateral triangle. Okay. Construct again equilateral PQR such that now each point lies on one side, right? So P lies on side BC, Q lies on CA, and R lies on AB. So we have to construct this triangle with ruler and compass. Okay. But in this, you will realize that actually there are infinitely many triangles. There is not just one triangle. If you think about it, in fact, you can start with any point on the line BC. And if you apply this logic here, P, because here point P was not special, it could be any point in the plane, right? So here I could choose any point P on the line BC, and if I apply the same procedure as this one, I'm going to get one triangle, right? So maybe this is my point, I'm going to get a triangle like this. So I'm going to have infinitely many triangles like this, and I can construct all of them using the process which I mentioned above. Okay, but I can ask two, three different questions here. Like first question I can ask is construct the smallest equilateral triangle. Which has the above property. So out of all these infinite possibilities, which equilateral triangle will be the smallest in size? So smallest means the length is as small as possible, length of one side. So this is like a variation of this original question. So let me call it question 1A. Okay. So if question 1 is just constructing the equilateral triangle, question 1A is construct the smallest equilateral triangle. So that is a very different question. Okay. Just to illustrate this on GeoGebra, that what that may look like. So as I said before that I could take any point uh, P on this line, and if I repeat the procedure that we discussed last time, that if you remember what we want to do, we want to construct triangle PQR such that Q is on one line, uh, R is on the other line. And by the way, let me delete the. I always like to denote it as lines, not segments. Okay. So if I rotate one line, let us say I rotate line AC anti-clockwise, so that it becomes. So I rotate anti-clockwise 60 degrees. So wherever this rotated line meets my other line, so we said that this has to be the point Q, right? And so if I take Q as my center and I draw a equilateral triangle, You see, nicely the third point is going and lying on the third side. So that is not surprising. And now if I vary the point P, you see that every point P will give me one equilateral triangle, but in my diagram, roughly speaking, it looks like this position is giving me the smallest triangle. But how to construct that with ruler and compass? That is the challenge. Okay, so this is one question to think about. Construct the smallest equilateral triangle PQR. Okay. And now, can you think of some variations? Like instead of triangle, what about quadrilaterals? Can I ask the same question for quadrilaterals? Like, for example, let me ask question 2. Inscribe a square inside a given triangle. So what does that mean? So now I want a square inside my triangle. But of course, the difficulty is square has 4 points and I only have 3 sides. So I will have to maybe over describe. Maybe two of the vertices lie on the same side. So let us say I'm interested in a diagram where it looks like this. Okay. So PQRS. Okay. So I have PQRS is a square such that P and Q lie on one side and remaining 2 points lie on other two sides. So this is another question which you can think about. Or you may think that if I'm taking a square, why would I put it inside a triangle? Inside a quadrilateral. So I'll take any quadrilateral and now my demand is that, so if I call this quadrilateral ABCD, I want a square PQRS like this. So each point lies on one side. Okay, so question 1A, then question 2, and finally question 3. Okay, we are going to discuss all of these next time, and all of them have some elements of transformation. Some of them can be done without transformation also, but we just for because we are in this topic, like to focus on transformation only. But like there is a lot of wide variety of problems which can be done with transformation. So we are just getting started with all of that. And in somewhere along the line, we will also require more and more complex numbers. So as and how required, I'm going to keep referring to the complex number theory also. Okay, but I'll stop early for the day. Any questions or doubts about this or all the theories we discussed today? Okay, if not, then that's all.
Nice, sir. Thank you, sir.